Hey, welcome back to Calculus. In this video lecture, we're still in section 2.7. I'm just going to do some more examples of computing derivatives. I'm not going to write the definitions of derivatives here. If you need to refer to those, you should look in your book as you're watching this, or if you need to go back and look at the previous video, but it's probably easier if you jot them down on a piece of paper next to you as you're working through these examples with me. Okay, so let's just get going. The first example, I've got a function g of x, it's 1 over x, and I want to find the equation of the tangent line at 3 comma g of 3. So I'm trying to give you variations on the themes of these questions, but equations of tangent lines, like we looked in our previous video, that means you need the slope and you need a point. The point was handed to you here. We need to compute g of 3. G of 3, g takes its input and divides by it, so g of 3 is a third. So our point is going to be the point 3 comma 1/3. What's the slope? This is the concept from the calculus course. The slope is the derivative. This function's called g, so I'm going to call it g prime, and that's g prime at 3. Yeah, I need to do it at the input variable where the point of tangency is happening at this 3. So we're going to use this g prime of 3 to compute, or we're going to use the limit definition of derivative to compute g prime of 3. So let's get going. G prime of 3, I'm going to use the first of our two alternative definitions for the, maybe you should try the second one, so see if you can compare and contrast the algebra. So G prime of, excuse me, not X, G prime of 3 is equal to, by definition, it's the limit as X goes to 3 of G of X minus G of 3 over X minus 3. Right, so that's our limit definition of derivative, first form of it. And now I'm going to use what this function g is. G is the reciprocal. So that's the limit as x goes to 3 of, well, 1 over x minus 1 over 3 over x minus 3. Maybe you recognize this was one of our examples from when we were talking just about limits. The reason I wanted to teach you about limits is so you can compute these derivatives. So I won't belabor this here too much. I'm going to get a common denominator in that numerator. Well, first of all, this 1 over x minus 3, I'm going to, instead of dividing by x minus 3, I'm going to write it as the reciprocal. And then that numerator, 1 over x minus 1 over 3, if I get a common denominator, that's 3 minus x over 3 times x. This, just like we did in the previous lecture when we were looking at this just as a limit, 3 minus x over x minus 3 is -1. So I'll cancel those factors. That cancellation is valid as long as x isn't 3. And now I can just let x equal 3 and get my limit. It's -1/9, minus 1 over 3 times 3. All right, so that's my slope. That's my slope. So now what do we got to do? We got to write down the equation through the point 3 comma 1/3. Let me just remind you, instead of scrolling, that our point was 3 comma 1/3. Our slope is -1/9. So let's use the point slope form. So what do we got? We got y minus the y coordinate that we know. This is the tangent line I'm writing down. Y minus the y coordinate I know is my slope, times x minus the x coordinate that's known to be on the line. And then again, I like to do a little bit of math just to clean this up, put it in y equals form. So let's see what we got. -1/9 times x, and then we'll have plus 1/3. Yeah. And if we add another 1/3 to that, you get -1/9x, adding 1/3 to both sides. 1/3 plus 1/3 is 2/3. So this should be the equation of the tangent line to the graph of g equals 1 over x at x equals 3, right? Let's flip over to Desmos and see if we got it right. I want to get you in this habit, so I'll try to practice my own advice. So here's my Desmos screen. It's waiting for us. It's ready to go. So I'm going to plot the function first, 1 over x. Hopefully it's in your library of functions. It's getting plotted in purple here. Looks like the function 1 over x to me. And then let's plug in this tangent line. We just said it was -1/9. So if I do -1 divided by 9, and then make that my x variable, and then we have to add the y-intercept was 2/3. All right, so it's drawn it in black. We can put in our point if we want to label it. It's the point 3 comma 1/3. Throw a label on there. It's going to draw that point in red. And again, zooming in, It looks to me like our answer is correct. That black line looks tangent to that purple curve at the point 3 comma 1/3. So good job. All right, nice. Let's do another example. Coming back to my whiteboard. Switching back this way always takes a little bit longer because I have to talk my iPad into sharing its screen, but there we go, we're back. Let's look at a second example. Pause these videos and work at your own pace. Work ahead of me, and then look at what I do and see if you did the same thing. That's the best way. As a student here, you're looking at the problem. Work ahead of me and see if your instinct was correct. So this time, what's the example about? I've got an object that moves. H of t is the square root of t plus 1 feet in t seconds. And what's my question? What's my keyword? Velocity at time equal 15. All right, so how does a calculus student translate this? What are we being asked to do? We're being asked to find h prime of 15. H prime of 15 is what we want to know. Let's use the alternative definition just for variety this time. So, well, actually maybe not, because my function's called h, and in that alternative definition, the variable's called h. I didn't think about that, and I don't want to go back, and I don't edit these videos. So I'm going to use the non-alternative definition. I'm going to write that this is the limit as, what's my variable called? T. So it's the limit as t approaches 15 of h of t minus h of 15 over t minus 15. All right, so that's the limit definition of derivative. Now let's start looking at the details for this h. So that's the limit as t approaches 15. H of t is, well, it's the square root of t plus 1. What's h of 15? If you plug 15 in for t, you get 15 plus 1 is 16 under the square root. The square root of 16 is 4. So I'm just going to write a 4 there for that h of 15, and I have to divide that by t minus 15. And then pause the video. I'm not going to go slow here, but you should pause it. What technique do you need to use to evaluate that limit? We saw limits like this earlier in chapter 2. It's got a difference of square roots. So to evaluate that limit, I'm going to multiply by the conjugate. So I'm going to multiply this expression by t plus 1 plus 4 divided by itself. That's not going to change my expression. But remember, this conjugate, when you have a difference of square roots like this, it's going to algebraically allow us to simplify this thing. So got to write the limit again. I'm not ready to take it until I let t equal 15, and this denominator, t minus 15, is forbidding that. But what do we got here? Well, when you multiply something by its conjugate, the cross terms cancel. So you're just going to get the product of the leading terms. Square root of t plus 1 times itself is t plus 1. Those cross terms cancel, yeah? Minus 4 times this thing plus 4 times the same thing, they eliminate each other. So I'm not even going to write it. The last term will be minus 4 times 4. That's minus 16. And downstairs, I've got a t minus 15 times the quantity square root of t plus 1 plus 4. I'm not going to expand that out. I can see in my numerator that I've got t plus 1 minus 15. That's minus 16. That's t minus 15. So those guys, as long as t isn't 15, which it isn't, because I'm taking the limit at 15, they cancel. So if we simplify this up, we'll be ready to take the limit. It's the limit as t goes to 15. My numerator is simplified to just be 1. The denominator is the square root of t plus 1 plus 4. And now you can let t equal 15 without dividing by 0. You're going to get 1 over 4 plus 4, or 1 over 8. Yeah, and that's 1 over 8 what? So let me scroll back. Sorry, let me just remind myself that this was talking about finding the velocity of an object whose position was measured in feet and time was in seconds. Yeah, so the units on this thing would be in the numerator. The change in feet is in feet. Change in time is in seconds. So our units on our velocity should be feet per second. So I'm going to answer that my derivative, my velocity at time equal 15 is 1/8 of a foot per second. Okay, cool. All right, let's do one more. one more example just to practice this. Try to keep the video short, and then I hope you're going to do those textbook problems as in addition to the activity and sort of become proficient at these things where we are already proficient at limits. So we're just taking limits of this limit definition of derivative, this difference quotient, people sometimes call it. Okay, so what do I got here? In the context, I've got a quadratic polynomial, x squared minus 3x minus 5 in our third and last example. And once again, somebody's asking me for the equation of the tangent line. All right, so when I see equation of a tangent line, what my brain is prompted is I need a point and I need the slope. Okay, what's my point? Well, I'm finding this tangent line when x is 1. What's the y coordinate? Well, that's f of 1. Pause the video for a second and compute it. What do you get when you plug in 1 into x squared plus 3x minus 5? I'm going to say that you get minus 1. So that's the point. What's the slope? The slope is f prime of 1. F prime of 1. We're always doing this. The input variable dictates everything. The output variables can always get computed. So I need to know the slope when x is 1. I need f prime of 1. All right, let's try the alternate definition with the h will actually make this algebraically more complicated. So let's again compute this thing by definition of the first kind. So this is going to be the limit as x approaches 1 of f of x minus f of 1 over x minus 1. That's the limit of the limit definition of derivative. I said it earlier, maybe I could point at it right here. This thing in red brackets, it's called a difference quotient. Yeah, change in output over change in input, difference quotient. Quotient meaning division. Okay, so what's f here? Trying to model good notational behavior. F of x is, oh, I can't see it anymore. I got to scroll. It's x squared plus 3x minus 5. We already computed f of 1. We said it was minus 1. So be careful here. We got to subtract that minus 1. Okay. Now let's just do a little bit of algebra simplification. Keeping my limit going along for the ride. I've got x squared. I've got 3x. Minus 5 plus 1 is minus 4. So now check that limit. Check the denominator. Letting x equal 1, of course, gives 0. What about when you put x equal 1 up here? You get 1 plus 3, take away 4. That's also 0. So that thing must factor. That numerator must factor. And in fact, there's a hint. It must factor into x minus 1 times something. That's why plugging in 1 made it 0. So what does that something have to be? Well, negative 1 times what is negative 4? It has to be positive 4. So you can check that factorization, and as long as x is not equal to 1, those factors will cancel. X is not equal to 1 because I'm taking a limit at 1. So we get, this is the limit as x goes to 1 of x plus 4, which is 5. As x approaches 1, x plus 4 is going to approach 5. So there's your slope. That's your, what was the name of this function? I forgot it already, f. That's my f prime of 1. It's my slope. The point was 1 minus 1. I remember it, so I won't scroll. So all you got to do is write down the tangent line. Come to my office hours if you want to practice or you want to review with me. It's a fundamental skill, being able to write down the equation of a line, given its slope and a point on it. So this is the second time we've done it in this lecture, so I'll just make quick work of it. It's y minus the y coordinate that I know is the slope times x minus the x coordinate. So that's y plus 1 is 5x minus 5. And if we subtract 1 from both sides of that equation, you get y is 5x minus 6. And we're going to end this video by flipping over to Desmos and seeing if everything we're saying makes sense. Or looks right, rather, not makes sense, looks right. That's what Desmos can do for you here. So let's go back. I've got to clean up a little bit in my Desmos screen. I'm done with this previous example, so I'll just get rid of all that stuff. And let's start by putting in our function. Our function was x squared plus 3x minus 5. So there's that thing, and it's not a very good view of it. If I zoom out a little bit, certainly it looks like a quadratic function, nice parabola. And now let's put in what we found for our tangent line. What did we say our tangent line was going to be? 5x take away 6. It's drawn in green. Where's this point of tangency supposed to be? 1 comma minus 1. Label it. What do you think? Did we do well? Zoom in a little bit. The question that you should be asking yourself, if you did these calculations, would you look at this picture and say, I got that problem right? It looks like it to me. It looks like that line is tangent to that curve. Okay, I hope those were useful. I hope you're going to do the activity. I hope you're going to do all of the problems in the section 2.1 textbook homework. And when you're done doing all of that, you'll feel confident about this and you'll be ready to take a problem like this on your exam. Thanks for listening.